So, I wanted to make a quick video about the Euler-Lagrange equation, specifically in physics, because it's a very advanced looking equation and the mathematical derivation for it can be a little bit tricky for people that don't have the strongest mathematical knowledge. And so I wanted to give a physical example of it and how it stems from one of the simplest equations of physics, quite simply. So let's consider a very simple situation where one holds a ball in the air and drops it. This equation here describes the energies acting on the ball free of any resistive dissipative forces. So we have the gravitational potential energy is supplied to the kinetic energy, and that's why the ball moves, right? But let's say we wanted to rewrite this equation in terms of forces rather than energies, because, forces are vectorial and we can gain perhaps a better geometric picture that way. There are many applications to it, of course. So we can, we have one particular expression for force, which is F equals dp dt. Force is the change of momentum, right? If momentum changes, then a force is acting on the object. So maybe I can restructure this equation here into just one expression, right? So I can obviously do that by just minusing, mgy from half mv squared, and that gives us just one thing is equal to 0, right? I can designate that as its own thing. We can call it a functional, which is just like a function of x or y, but it takes in a function rather than a variable. So we call this the Lagrangian. So L, with this fancy L, it's a function of y, it's a function of y dot, and because it's a function of y dot, it's also a function of time. And that's going to be equal to 1/2 mv squared, or y dot squared, so I'll make it y dot actually, minus mgy. And that's of course equal to 0 by itself. But that's not the point. We want one thing to mess around with. We don't want, two sides of an equation. We want one thing. So what can I do to this Lagrangian to find an expression for force, right? I'm looking around, I'm thinking these are energies, right? Well, we know from normal physics that force is the gradient of the potential of the respective potential field, right? So gravitational potential is, dv dr, dv dx, dv dy, depending on whatever dimensions you're working in. So we have a potential here. So if we differentiate our Lagrangian with respect to position, just y, not y dot as given here, this side is going to go away, right? Because it's just, there's no y there, it's just y dot. And the y here is going to go away, leaving just the minus mg, right? So differentiating this with respect to just y is going to give us a force, mg, minus mg. So that's our left-hand side. We can write dl dy. That's a force. But what about this dp dt? Well, how can I get momentum out of this Lagrangian? I can, I'm looking around. What happens if I differentiate with respect to y dot? Because momentum is mv. If we want it linear in v, then we can differentiate to get rid of that too, right? So if we differentiate this with respect to y dot, not differentiating with respect to a variable but to a function, just as we did there, then the 2 comes down and it becomes mv, right? Just like differentiating half mx squared, right? It would be the same thing. So that gives us a momentum. 1/2 my dot squared differentiated with respect to y dot gets us my dot mv. That's a momentum. So then if we differentiate that with respect to time, we get a force as well. So surely this equality is just d dt, differentiating with respect to time, of the derivative of the Lagrangian with respect to y dot. And would you look at that? That's the Euler-Lagrange equation. Just like that, just by considering energies and considering changing them into forces to give us a different picture to work with. That's what almost all of maths is about, is just changing perspectives to make things easier. If you can master the act of changing a perspective, then you'll go so unbelievably far in whatever you choose science-wise, and I'm sure that would apply to anything else as well. So whilst one would derive this normally using the principle of least action, I don't know if you can see that, you can derive it very quickly by just considering a very simple situation and changing your perspective from scalars, energies, to vectors, forces and momentums. So there you go.